All right. So this is a project I've been working on kind of off and on for the past few months. Um, and basically what you're looking at here is a Trimble GPS antenna. Um, this is what's called a geodetic antenna. This one is quite old. It's date code, I'm not sure if you can see it. It's the 18th week of 1990, so it's older than I am. And it was paired with some of the Trimble 4000 series receivers from the time. And basically the idea was that this would be used for taking long-term geodetic measurements, or you could use it, I think it was sold to do real-time kinematics in the field, some other stuff like that. It's a good antenna. I got a good deal on it. The actual antenna is the silver patch here in the middle, and it's an L1 and L2. It was just sold as a GPS antenna. Of course, in 1990, there was only GPS or Navstar. But it does receive the other L1, L2 band constellations just fine. And even some L5 stuff slips through sometimes. But what I want to do with it is, you can see there's this big cavernous enclosure at the bottom here, and I can try and overlay some photos to make it a little bit clearer what exactly we're looking at. And I can also, while I'm talking, disconnect this. It has a very large low noise amplifier in it because it's all, discrete components. I don't believe there were any integrated LNAs back then. And that needed a pretty big enclosure. And I guess because they figured space and weight wasn't a concern, they gave this thing a giant base. So let's take a look at it here. The reason for this big metal plate, by the way, this is the ground plane. And effectively what it does is it prevents signals that hit the ground and then bounce back up from being able to be received. Basically, if you look up multipath in GPS, it causes all sorts of problems. And when you're taking geodetic measurements, signals that bounce up from the ground are especially troublesome. And so that's what this big plane is for. There are a couple different versions of this antenna. I apologize, this is unpleasant. Some of which have a removable ground plane. This one is integral, and it's frustrating because, so this unit is the actual GPS antenna. You can see the SMA connector on the bottom. I'm not entirely sure what this is made of. This bottom plate is metal, or at least looks metal. This top plate looks a lot like an FR4 type composite. It's something like that. I don't know for sure. And then I can lift off. So all the fun stuff is actually attached to the ground plane because this box here is the LNA itself. So if I lift that off, you can see that on the bottom, got a couple cables running through because I've already done a little bit of testing with this. Pull these all the way through here. And my goal is effectively to have this operate as, either an RTK type base station to be used, in real time with rovers, or to use it as a geodetic receiver to take static measurements. So here's the actual base unit. This is quite heavy. It's not magnesium, or if it is magnesium, it's just very dense magnesium. And it has this little indicator on the bottom for humidity. And the lavender dot is supposed to indicate the highest relative humidity, and they're all kind of pink. I want to get rid of this. I have yet to find a pair of pliers big enough, and what I've used to torque on it hasn't moved it. But you can see the threads. You can see how it's threaded in there. I don't know if this is intended to have any dehumidifying characteristics or what. But as you can see, there's a lot of space to work in here, even with that thing being in the way. This hole here on the side is where the Type N connector stuck out. And I've just been using it as a cable pass-through. Eventually, I would like to put some sort of a gland in there. But this is what the actual underside of the unit looks like. Pardon the very messy temporary cable routing. Will that focus on that? Maybe. Basically what we've got here is that the metal box that's the base plate is the LNA. This red board is the GPS receiver. This is a SparkFun receiver using a Quectel LG290P. And then this little green board is the bias T, basically power injector. And effectively all it does is it pushes DC into the LNA. Folks who are familiar with this will know that most GNSS receivers actually have a bias T built into them and provide voltage. This one, for example, spits out 3.3 volts, which for most modern LNAs on GPS antennas is perfectly fine. This particular one wants between, I think it's like 7.2 and at least 12, maybe as high as 18. I don't remember exactly. But 3.3 does not cut it. So that's why we have an additional bias T here. And it has a capacitor on it that basically prevents any DC from coming downstream, but allows RF to flow, no problem. Just, it's the same as the bias T that's on the board. It's just a discrete component because I need to be able to feed in my own voltage, which is the purpose of what I'm digging into today. So, like I said, this thing is rated for the minimum. Yeah, okay. I'm just looking at the document I pulled up on the screen here. The minimum is 7 volts. The maximum is 28 volts. And per some testing that UNAVCO did, it seems like the current and voltage are somewhat proportional, or they scale. So if you feed it, where is it for this? Yeah, for the 15532, 7 volts will pull 52 milliamps, 12 volts will pull 87 milliamps. I don't know if that means that 28 volts would pull, near 200 milliamps. I'm not sure. I'm not going to test it at that. I don't want to put that much power into it anyway. Testing at 12 volts has been fine. So I want to test with a slightly lower voltage, in particular 9 volts. I did find a spec of the Trimble 7000s or 4000s, and they fed 9 volts. And so what I'm going to test out is this little guy. Let's see if we can do a zoom here successfully. This is just a very simple boost type voltage regulator. But specifically, it can take 3.3 volts in. I think it's 2.6 to 4 volts is what this particular model is rated for. And then this is the 9 volt model. It can go up to 12, but I want to try it with 9 volts. These were real cheap, as you probably imagine. And they're, kind of the same pinout as an old style linear regulator, where you have voltage in, voltage out, and a common ground. And so my plan is to drive this thing with the brains of the system. So it's going to be, the GPS is going to feed its signal into something like one of these. I don't really know. Like I said, I haven't decided for certain. But, we have ESP32, kind of your standard if we're working with Wi-Fi or Bluetooth. And then I have a LoRa module, and I believe this is just an Arduino, at Mega 328P or something. Trying to look at looks like 32U4. Yeah, I guess that makes sense because the model is LoRa 32U4. Anyway, so my thinking is to effectively have this thing set up such that it either does real-time kinematics and just spews the correction information received from the GPS directly over the 433 megahertz for just local use by a rover, or uses something like this. This is just a micro SD card shield, and just logs to a file. I've looked at things like the SparkFun OpenLog. There's a lot of really nice options out there, but these are what I have on hand, so this is ultimately what I want to try and use. But the thing that I like about both of these boards is that they have single cell LiPo controllers on them. And so we can really easily use a little pack like this. This is, 800 milliamp hour? No, this one's 1,000 milliamp hour. So it's not a ton of power. Of course, bigger ones exist. And if this ends up working, I could, use something like a couple of 18650s or one of the bigger lithium iron phosphate packs, something like that. But I'm curious to see, if I attach this cell to one of these boards, these do spit out a regulated voltage. This little guy, I think in this case, I'll probably just tap the battery voltage directly so that we're not putting any load on the regulator. And then I want to take a look at what the stability of the power coming out looks like. I would imagine it's pretty clean, but I'm curious to see because you never know with these cheap boost converters how messy it's going to look. And if it looks really messy, is that something I can just put a filter, a smoothing capacitor on? Or is it going to be too messy for the LNA regardless? Or is the LNA generic enough that it will accept anything as an input? So anyway, that's kind of what I'm looking to test here. So what I'm going to do is attach wires to our regulator here and tack a couple of wires onto one of our boards. And then that's why we've got the scope humming away up here, because I want to just take a look at the output briefly and, see what it looks like. So yeah, I'm going to go ahead and do that. I'm going to get those wires tacked on and see how that looks, see if that'll be sufficient. Yeah, and then we'll take a look at what it looks like on the scope. Unfortunately, I haven't done anything with the scope in a while, so I didn't know where all my odds and ends are. But unfortunately, I don't know where the clip is for my probe. But I might know where my BNC to alligator clips are. So I'm going to take a look around for those. I also may know where the clip is, so I'll take a look around for both of those. And then, yeah, solder up those wires, and then we'll do some testing. Okay, so the setup is admittedly, a little bit ugly. And I just need to kick over the tripod here. And we did have to do a scope swap. Curiously, all the soft buttons on my HP scope were not functional. So I don't know what's going on there. Oh, and did we just lose our... Yeah, it's, like I said, it's not optimal. It's a little janky. It's a lot janky. Just because I don't have a clip. I couldn't find the clips. Anyway, it's very simple. We've got the LiPo feeding into the LoRa board. And then I've just tapped off the battery voltage, which is reading like 4.2 volts. And I verified, I pulled up the spec sheet for the regulators, and they're 2.6 to 5.5. So 4 point something volts is perfectly fine. And then the 9 volts out is just running into the scope here. And if I try and get this looking at the scope, you can see it's fine, basically. You know, there's a little bit of noise. I'm pulled in pretty much as close as it'll let me. You know, you can see a little bit of wiggle, but it's really not that bad. I don't think it's going to cause any problems. And it's the sort of kind of flickering that I would have expected anyway. What I was worried about was chopping that you sometimes see with older buck and boost converters. Granted, there's no load on this, so I'm going to do the same thing when I hook it up to the LNA here. I'm going to try and measure load and see how much current it's actually pulling at 9 volts, and then also see if I can measure this instability, or measure what it looks like at this voltage anyway. So it's going to get a little bit messier here, but let's kind of give that a shot. Okay. So let me stop this again, and then I'll pull out the LNA and get everything hooked up and see what happens. Okay, we are ready to do a little bit more testing. Because I don't have a clip for the oscilloscope lead probe, I'm gonna do current first and then see if I can branch out from there. So I'm gonna measure current on the ground rail, so you can sort of see if I can pivot this. So you can sort of see here's the ground coming off of the bias T, and it's just sort of attached. I really should know where my alligator clips are, but I've got that attached to my ground probe of my meter. My meter's in current mode, and so I'll just touch the positive probe to a ground source, probably the micro USB port, and then that should complete the circuit and power the LNA. I have the antenna attached just because I'm assuming the LNA wants that 50 ohm load there, but I don't know for certain, but I don't want to test without it. So, and we know it has 9 volts, and we know the 9 volts is relatively clean, unpowered. So let's power it up. All right, so that's got power, but I want to verify that it does first. So I'm actually going to switch this back to DCV, and then what I'll do is measure the center pin. Actually, you know what? I won't measure. That's a little bit too risky. I'll measure it right here. Oh, right. We're not going to be able to measure voltage there because the ground is not completed, and that's connected here. All right, never mind. Forget it. We're not going to bother with that. Switch it back to current. Like I said, it's been a while since I've done anything like this. And okay, so that's really not bad. 65 milliamps. Not bad at all. So then the question is, can I attach this guy such that I can get, I want to see if I can get a permanent reading. So I would like to see both the stability of the power and the current. So this is how we are going to approach that. measure this? I think I can measure this from where I was intending to measure it previously. Right there. Yeah. So I don't know how easily you can see the scope. But it's, a little bit jittery 9 volts, a little bit jittery me, and, 65 milliamps. Cool. And I know this test setup is far from optimal, but it is just a test setup, and it confirms 65 milliamps at 9 volts. Gets that LNA going. So now the real question is, how does it perform as a GPS antenna with that 65 milliamps and 9 volts? So, how do I want to do this? Because all of this stuff needs to be encapsulated so that I can kind of put it in the enclosure a little bit. What I was using previously, which I didn't show, I should have, was just one of these little enclosures where you get 8 AA batteries and 12 volts. It's got a little power switch, barrel jack. And I had that running to just a barrel plug, and it worked fine. But this sort of setup would be better because that means that whatever is powering the transmitter and the GPS can also be powering the bias T, the LNA. And I think I just need to reconfigure this a little bit. And what I might do is attach the power. It doesn't need to be powered anymore. I can attach this voltage regulator to the underside of the bias T, just to kind of shorten up the runs a little bit. And I don't think it needed to be attached to the GPS. I wanted it to have the 50 ohms kind of on both sides. Because I do think I'm still going to feed it that 3 volts with this kind of a setup. But I think just due to the size of this board, it'd be trivial to put a little piece of double-sided foam tape on the underneath and then just stick it to the bottom of the LNA or of the bias T. I don't know why I keep calling that the LNA. Yeah, all right, so now that we know proof of concept that this works, tidy it up a little bit more so that we can do a field test. All right, so I made a kind of obvious realization, and that is that for right now, I do not need to incorporate this guy at all, or the LiPo. The reason for that is because I want my initial testing to just be over USB for my initial setup and everything. And that's probably because I'll use a Raspberry Pi, at least on sort of at the onset. And so I'm just going to use USB, which means I can just pull power off of the GPS module. And the main thing I wasn't sure about is if there was going to be sufficient overhead from its LDO. I didn't want to swamp that. And thankfully, because this is SparkFun, they make that information available. So the voltage regulator on their LG290P board is an RT9080, and they specifically say that it can source 600 milliamps. And the LG290P peak pulls a... Did I misspeak? What am I... sorry. Okay, yeah, I was misreading across milliamps and milliwatts. The LG290P pulls about 100 milliamps at the most, you know, around 300 milliwatts. So if it can source 600 milliamps and I'm going to pull an extra, call it 70 on top of that 90, that's still plenty of overhead. And I figured that was going to be the case, but with smaller components like this, it's a good idea generally to test it just to make sure. So what I did is I attached the regulator to the underside of the bias T, and then I've just got a short jumper that's attaching ground and voltage output to the bias T. This is giving us a not super optimal ground loop because it means since I'm only giving it power from here, I'm not also connecting the ground. There's a little bit of a ground loop going basically from here to this, through this coaxial connection over here. But since it's just DC power, it's not an RF ground loop. It's fine. You know, if it were to be an issue, I could run a second ground wire right there. But it's, again, I don't anticipate it being any kind of an issue. But that means this should be good to go for initial testing. And I could sort of handhold it like this. And I might try that. Unfortunately, the tablet that I was using is at work. There's a really nice program called SW Maps, I think. And it supports USB connected GPS receivers, which is quite nice. So I could do that. But for right now, I think I'm just going to leave this as is and plug it into my laptop. And I don't think I'm going to handhold it, though. I think I am going to reassemble this in the box just because I don't want to risk knocking anything, pulling anything. One thing, where's my pointer? Here, you know, you can see the double-sided tape there. It's, you know, maybe 2 millimeters thick. It's at this kind of angle, and there's a little bit of clearance between it and the top of the quick connector. You know, that's all plastic. I'm not really worried about that shorting against anything. But once I get this working and I'm happy with it, I'll hit it with a shot of like hot glue on the side just to kind of keep it from moving around a little bit too much. Just to help secure things a smidge. But otherwise, I think this should be good to go for its initial test. Like I said, I just need to button it back up. But then I'll only need to power it from USB, which will make it a lot easier to test with. So yeah, go ahead and do that.